look at this question. So we have a AC alternator. Okay, the way I tell them is this, the slip rings, and well, yeah, sometimes we call it AC generators, but yep. And the question asked me, is the magnitude of flux increasing or decreasing? Okay, increasing or decreasing. So the magnetic flux has a formula B times A. Okay, the magnetic field doesn't change in this as it rotating clockwise from this position. The magnetic field doesn't change. Okay, the only thing changes will be the area. So just be aware. Just be aware. The area is the area, the cross section area here. Okay, so when it's on a slide, we talk about this area. We talk about this part of the area. Okay, so as it rotates, as it rotates, sorry, if I put it down, the area is the perpendicular area. So as it rotates from position 1 to position 2, okay, the perpendicular area increases. Okay, so the magnetic flux increases. Down. Now look at this question here. So in this question, we need to find the direction of current. Okay? Just remember, when we need to find the direction of current, you need to use your Lenz's law. Okay? Lenz's law. Now look at what's happened here. Okay? So as we rotate this coil at this position, there's a force acting upwards on the left hand side and force acting downwards at the right hand side. So the coil is not happy. The coil will always try to resist the change, resist this force. So what the coil wants to do? The coil wants to push it downwards. So when we use our Lenz's law, make sure in this case, put your palm. When you use your right hand rule, put your palm downwards, because this is what the coil wants to do. Okay, so the coil pushes the force downwards, and lies your finger in line with magnetic field, you figure out the current actually, let me use different, the current actually goes in this direction. Okay? So the current goes in there, and come out there. So that's the direction of the current. And indeed. So when they ask you to explain your answer, go to your cheat sheet, copy down Lenz's law, and telling them that the coil wants to generate a force acting opposite to the direction of the applied force, which is downwards. Thus, a current goes in this direction. Okay. With that's it. Question 3. Sorry. We have a coil of 50 loops, so n equals to 50. It's rotated at the rate of Okay, it's rotated 4 times per second, so it's 4 hertz. Okay, so yep, our period is going to be 1 on 4 second, which is 0.025. Right, 0.25 seconds. The magnetic field is this. The coil can be treated as a square side of 10 meters. It's a square, so the area will be 0.01 10 centimeters times 0.01 10 centimeters, which is 0.0001 meters square. Be careful with all those units. So what will be the average EMF? Okay, so we're going to find the voltage RMS, the average EMF of this basic generator. Okay, so what we do here is use Faraday and Lenz's law. The induced EMF is minus n times the rate of change of magnetic flux over the time. Okay, so let's put everything in. Remember this value here by Lenz's is calculated is the RMS value. Okay. This is the RMS value using this equation. So n is 50, so minus 50. Now the magnetic flux. So if you look at your nose, okay, now we need to find. Basically, what we need to find is we need to find the maximum change in magnetic flux over time. So assume the coil initially is in line, is in parallel with the direction of the magnetic field. The coil has the magnetic flux is 0. When the magnetic flux is maximum, it becomes like this. So the change in magnetic field, magnetic flux, will be the maximum magnetic flux take away the minimum magnetic flux. Okay. In the case of an AC alternator, the minimum will be 0, the maximum will be B times A. Okay. B times the maximum area, okay, which is 0.12. Okay guys, yep, sorry, I think I made a mistake somewhere, here. Yeah, I made a mistake with the area. So yep, the area is, the side is 10 centimeter, which is 0.1 meters times 0.1 meters. 10 centimeter. 100 centimeter is a meter, so 10 centimeter is this. So the area will be 0.01 meter square. Okay. So the maximum magnetic flux will be 0.12 Tesla times 0.01. Okay, take away, yep. And the maximum change in magnetic flux, so is this. Okay, so in a AC, so in an AC alternator, when they ask you to find the RMS value, okay, you always use the maximum change in magnetic flux. Okay, which is the maximum take away the minimum, the maximum take away 0, the minimum is 0, and yeah, that's the change in magnetic flux. Okay, the maximum change. Now, what we need to do next is divide by the change in time. The frequency is 4 Hz, the period is 0.25 seconds. However, if you look at the diagram, okay, the time for the coil to change from minimum to maximum or from maximum to minimum, okay, from position 1 to position 2 is, say that's position 1 here, position 2 is not a full period. Okay, it's a quarter of period. So just be aware, okay, the change in time, okay, when we're dealing with AC alternator is always a quarter of the period. So it's 0.25 divided by 4, which is 0.0625 seconds. Then put it in. Okay. So if you have, yep. So if you put all this value in, you have minus 0.96 watt. Okay, but we finding the average. Yep. So in an AC alternator, this formula is for average voltage. The average voltage should be a positive. It's always a positive for AC current. So just change it to 0.96 watt. Okay. So this formula, okay, yep. So yeah, I should tell you this before. So this formula, okay, used a little bit differently in AC alternator. Okay. So in AC alternator, normally just use it normally, but if it's AC alternator, okay, the change in magnetic flux will be the maximum change. Okay. The change in time is quarter period, it's not a full period. Okay. And once you find out the value, okay, voltage RMS must be positive. Okay. Okay. If your value is negative, just get rid of it. So RMS is positive. Okay. And yeah, this is done. Okay. So please make sure you have this in your notes.